All right, let's dive into a truly monumental achievement in physics. This is work so groundbreaking, it's our pick for a future Nobel Prize, awarded here to John Clark, Michel Devoret, and John Martinez. What they did was build a bridge between two completely different realities, the world we see and touch every day, and the incredibly strange, invisible world of quantum mechanics. Let's get right into it.
Okay, so to really wrap our heads around this, we have to start with a basic puzzle, a real head-scratcher that sits at the very heart of physics.
So think about it like this. On one hand, you've got the world we live in, right? The world of classical physics. It just makes sense. You throw a ball at a wall, it bounces back. But then you've got the quantum world, and down at the scale of tiny particles, the rules get weird. A particle can literally just pop through a solid wall and appear on the other side. It's called quantum tunneling. And that brings us to the big question. We know a single electron can do this weird tunneling thing, but what about something made of billions of particles? Where does one set of rules end and the other one take over? Well, that's the exact question these laureates answered, and they did it in a way that changed everything. Now, to build that bridge between these two worlds, our laureates needed a very special, very cool set of tools. First up, you need something called a superconductor. And this is where things get cool, literally. When you chill certain materials down to almost absolute zero, their electrons do something amazing. They pair up into these things called Cooper pairs, and then billions of these pairs all start moving in perfect unison. They act like one single gigantic quantum entity. The second key ingredient is the Josephson junction. What you do is you take two of those superconductors and you put a tiny, incredibly thin insulating barrier between them. That little gap, that's where the quantum magic is about to happen. And this is basically what it looks like. You've got the physical junction on the left, and on the right is how physicists model it as a circuit. This tiny little device, that was their custom-built arena, where they were about to see something big do something that should be impossible. So with their toolkit all set up, Clark, Devoret, and Martinez got to work back in 1985. They were about to see if they could make their circuit take a true quantum leap. Now get this, because this is where it gets really mind-bending. The circuit they built was macroscopic. You could see it, you could hold it, and yet those billions of Cooper pairs inside were so perfectly in sync that the entire thing behaved like one giant quantum particle, described by just a single wave function. To picture what they were trying to do, physicists use this great analogy of a tilted washboard. Imagine the system is like a tiny ball, and it's sitting in one of the dips of this washboard. For their circuit, that dip is a state of zero voltage. Now, common sense tells you that ball should be stuck there for good. And these diagrams show you exactly what I mean. The picture on the left, that's the classical world. The particle is trapped in that valley. It just doesn't have enough energy to get over the hill. But the picture on the right, well, that's the quantum world. The particle's wave can actually leak through the barrier. There's a real chance it'll just show up on the other side. This is what's known as macroscopic quantum tunneling. But here was the tricky part. How could they be 100% sure that's what they were seeing? How did they know the system wasn't just getting kicked out of that valley by some random heat or electrical noise? They had to prove it was a pure quantum effect. And this graph, wow, this is the evidence. This is the absolute smoking gun. It shows the rate the system escapes from that zero voltage state versus the temperature. So at warmer temperatures, over on the right, you can see the line slopes down. More heat means more escapes. That makes sense. But then, look what happens as they get it colder and colder. See the data for the quantum junction on the left? The escape rate just flattens out. It completely stopped depending on the temperature. The system was tunneling out all on its own, powered by nothing but the laws of quantum mechanics. They had proved it. So, just to nail this down, the fact that the escape rate became constant at super low temperatures, that was it. That was the unmistakable signature they were seeing true quantum tunneling. It wasn't heat, it was something much weirder. But while they were proving this whole tunneling thing, they discovered something else, something just as profound about their big circuit. So the team started zapping their circuit with microwaves, and they noticed something fascinating. You can see it in these sharp peaks on the graph. The circuit would only absorb energy and escape at very specific frequencies. It couldn't just soak up any random amount of energy. It had to be a precise, discrete packet, a quantum. What did that mean? It meant that their circuit, this big visible object, had quantized energy levels, just like a single tiny atom. As the Nobel Committee put it, they had essentially built an artificial atom on a chip, a giant atom that you could actually connect wires to and control.
And this wasn't just some fascinating thing to see in a lab. No way. This experiment ripped the door wide open to an entirely new era of technology. You can draw a direct line from their fundamental research to the tech we hear about today. It all started with that 1985 discovery. That led them to realize they had an artificial atom. Those energy levels became the blueprint for the quantum bit, or qubit. And the qubit, well, that's the building block of a quantum computer.
You see those distinct energy levels they measured? The lowest energy state can be your 0, and the next level up can be your 1. The ability to build a circuit where you can create and control these quantum states, that is the absolute core principle behind today's most powerful quantum computers.
So this single discovery didn't just answer a question, it unlocked the door to a technological revolution. It's the bedrock for quantum computing, for developing unhackable quantum cryptography, and even for creating sensors so sensitive they can detect the tiniest changes around them.
In the end, what Clark, Deverett, and Martini showed us is that the quantum world isn't just for the invisibly small. They took its strange and powerful rules and brought them up to a human scale. And that leaves us with a profound question. If a circuit can be quantum, what's next? What other large-scale quantum surprises are still out there, just waiting to be discovered?